Okay, following the fitting of a unidimensional item response theory models, I'm going to fit some multidimensional IRT models to a data set called LSAT. It's actually the low school test, low school admission test, with 5 dichotomously scored items. The data, as you can see here, the data show the patterns of responding to 5 items in 32 patterns. It's actually, we have a binary scored item with a test including 5 items, so we have 2 powered 5 patterns. It's actually 32 patterns, and we have here the frequencies of these 32 patterns. The first thing that we are going to do is actually to make this item response pattern to a data table, the raw data table. So we are going to use the expand table function for the LSAT7 dataset. We just use this command for making our data table, and we actually name our data to data. It's as simple as that. So as you make your data to a data table, you can see here that the response patterns is actually converted to a data frame actually. So we have a raw data table here with actually 1000 examinees. We have 200 examinees shown here, and 800 rows of the examinees omitted, as you can read here for this data frame. If you want to have a descriptive item analysis and some classical test theory statistics for this data frame, you can use the item stat function here. If you run this function for the data that we made here, you have the Chrome batch alpha for this data set. It's somehow low for this data set. The reliability and internal consistency for this data set is actually lower than the recommended cut point, for example 0.6 or 0.7. You have also the mean of items. The mean of items in classical test theory actually indicate the item difficulty. So the lower the mean, the more difficult the item is. So You can see here that the fourth item is actually the most difficult item of the test. Overall, the mean of items, that is actually the proportion of correct responses for the examinees, are high for all items, so we are dealing with an easy test because most of the items reached correctly. Uh, in the last videos for item response theory models, I showed some unidimensional models that fits datasets. For example, the Rash model, the unidimensional model, the dimensional Rash model, one parameter logistic model, the two parameter and the three parameter, that which are the most common types of the item response theory models. Here we are going to run some two factors model. In general, as the ordinary factor analysis models, we have two kinds of multidimensional item response models, uh, such as the exploratory and confirmatory multidimensional item response theory models, like the ordinary factor analysis method. So we have mirt models that are exploratory, and the second is confirmatory. So, like the ordinary factor analysis models, where you have some theories for your item response data, you may want to apply the confirmatory models, either factor analysis or the multidimensional item response theory models. And in search for some measurement model theories, you may find it more relevant to use exploratory methods of factor analysis or multidimensional item response theory models. So here, for the first and for the default model, we use a multidimensional item response theory with two dimensions. It is null. It is worth noting that multidimensional item response theory models uh, with mm, two or at most three dimensions are uh, are usually uh, used in item response theory analysis, because more than two or three dimension models for item response theory models make the model so populated and make it uh, uh, a lot cumbersome and make it difficult to be converged. And uh, it is common to use two or three dimensions for multidimensional item response theory models. So uh, when you are dealing with some psychological or educational tests and skills that include more often two scales, it's more appropriate for you to do the multidimensional item response theory models. So if you call the mirt function or the mirt package that we use here, it is needless to say, as we did before, we just actually called the mirt package from the library function. So here we use the mirt function to do the multidimensional item response theory analysis. So if you do not uh, specify the item type here like this, the model automatically for default use the 2PL model. This is actually the two parameter logistic model. So if you do not specify which model you are going to use for the analysis, the mirt function use the 2PL model as default model. So here we just uh, specify the data. This is the LS87 data. The 2 is actually for the model argument here that show you how many dimensions your data should have for this analysis, and we call this multidimensional analysis uh, mode 1. If you run this syntax, uh, as you can see, the number of iterations uh, are a lot higher than the unidimensional models, because we are going to fit a two-dimensional mirt model. So the number of parameters that are estimated here are a lot more than the unidimensional model. If you ask for the coefficients of the models that we ran here. COEF function is actually stands for the coefficients of the model that we ran. So we name the model mod 1. If we ask for the coefficients of the models, uh, uh, here for the 5 items of the test, you have actually the difficulty for the items as D and the slopes or discrimination index for the items as A1 and A2. Since we are dealing with a two-dimensional item response theory model, it is expected that we have two discrimination parameters, and the difficulty measure is also the same for the two-dimensional model. Like the ordinary factor analysis methods, we have some rotations in multidimensional item response theory models. So for getting a more interpretable factor model, we just rotate the factor matrix, factor loading matrices to get a more interpretable models for factor models for our items in the test. So for the model that we ran here, we just use the up-limit rotation method here for the model 1 that we ran, and we use the summary function to get a factor loading matrices that is rotated through the up-limit methods of rotation for the factor loading matrix. As you can see here, for the rotated factor loadings, we have two factors and a communality measure that shows you the patterns of the loadings of the items for the two-factor model. As you can see here, the item 1 and the item 2 is actually the item 1 and actually the item 5 is loaded to factor 1, and the other items, the item 2, the item 3, and the item 4 are actually loaded to the second factor. The communality measure is actually about how much the factors explain the variances of the items. So the higher the factor loading, the more would be the H2 or the communality for this model. You have also the sum of the squared of the loadings for the two factors that in ordinary factor analysis models we call it eigenvalues. And these values show you from the Kaiser criterion the values actually about 1 shows that the factors actually are significant and should be considered for our factor analysis model. We have also the factor correlation matrices that yields you a correlation for the factor scores. We have a positive about 0.46 for the correlation of the two factors. So you can interpret the model through plots, through the plot function and the rotations that we made for our factor loading matrix. So if you plot the model 1 with the rotation method of Oblimin, you find plots like that. As you can see here, you have an additional ability level for the item for the test characteristic function. As you can see here in this two-dimensional plot, as the thetas for the two dimensions increases, the total score for the examinees increases here. So you have actually monotone two-dimensional model that shows you the two abilities, the theta 1 and the theta 2, which are the two dimensions or the two abilities that are needed for answering the test items correctly. As increases, the total scores also increases here, like the plots that you have here. It is actually a plot for the test score with the two dimensions that we fitted here. You may want to see the plot for each item. It is actually an item characteristics curve for the test items. You should use the item plot here to call the item characteristics curve for the two-dimensional model. The object is actually the model you are using here. The object is the mode 1, the model 1 that we fitted here. The item should be the number of the number of the item of the test that you are going to plot the item characteristic curve for the two-dimensional model. We ask for the first item of the test, and when you run this function, you have uh, the item characteristics curve for the first item in a two-dimension model. You have the first dimension theta 1 and the second dimension theta 2, and the uh, vertical axis of this two-dimensional plot is the probability of answering of the first item correctly. So as you can see here, as the theta increases for the two dimensions, the probability of the answering the first item of the test correctly increases, like here in this plot. You can do the same for the other items of the test. For the second item, here like that, the more S-shaped the model, the better fitted the model to the test. As you can see, the first item is more S-shaped, so the S-shaped plots, either for the unidimensional or for the two-dimensional model, shows the better fitted item for the test. You can do the same for the other items of the test, and like that you can see how the model and how the plot looks like for all of the test items. So you can see that the first item of the model and the fourth and the fifth items of the test are actually more S-shaped, so they are more fitted to the two-dimensional model. Like the unidimensional item response theory models, as you ask for the item characteristics curve, you may want to find out the information of the test and for each item of the test in the two-dimensional model. So in the item plots, if you specify the type of the plot that you want to info, Info stands for the information, and run the plot. You can see here that the item actually first item of the test is informative in the middle of the ability level. So in the average ability, the information of the items is maximum. So you find out that the item is the most informative, it's actually more informative in the middle of the ability level compared with the extreme uh, points of the ability level. You can do the same for other test items like that. The more fitted the item to the model, the better interpreted the plot for the item. So for the first and for the fourth and fifth item, you can find out a better information plot for the test. And the pattern is also the same for all of the test items, with a little bit difference for the fifth item of the test that is more informative in mostly the more informative for the uh, more skilled examiners. You can see here that the fifth item of the test is more informative for the examinees that have uh, that they are more skilled, and their skill are more than average of the level that you can see here. At last, for an exploratory multidimensional item response theory model, you can ask for the item fit statistics. In this regard, you call the item fit function here and specify the model that you run. We named it the model 1. And if you run the item fit statistics, as I explained before, you can see that at the 5% level or at the 1% level, because we have a large sample size and the significant level of the 1% is more logical to consider for item fit statistics. The chi-square, the degrees of freedom, the root mean square error approximation, that is an absolute uh, measure of the item fit statistics with a corresponding significant level for the chi-square is provided here in this table. As we have large sample sizes at the 1% level, the goodness of fit for the second item of the test is actually rejected for the two-parameter logistic model, and the other items are actually appropriate for the two-parameter logistic models with two dimensions. The root mean square of approximations that actually provide you with a absolute goodness of fit measure that is not sensitive to large sample sizes is provided here. The measures less than 8% or 0.08 tell you the item is fitted to the model. So as you can see here, except for the second item of the test, the other items of the test are well fitted to the two-dimensional, two-parameter logistic item response theory model. You can do the same analysis for a variety of models: the rash model, the three-parameter logistic model with one dimension, two dimension, or even more dimensions for a more lengthy test, and comparing them to the ANOVA function that I showed you before, that through the AIC and BIC measures, and even with chi-square based significance levels, you can compare different models with different item types and with different dimensions to find the optimum item response theory model for your test data. So it would be a good end for this session. You can do the same analysis, even more complicated and sophisticated modelings at home, and compare the models and find the optimum model for your item response data. Bye.